Hello.
Sir, you are audible.
Am I audible? I'm just trying to connect to Bluetooth device. Give me a second. Sorry, I just have to add this to my calendar. Otherwise, it's sort of. Sorry for the delay. Yeah, can we get started?
Yes, live started, sir.
So, hello everyone. Can we? I'm happy to take any questions if any of the students have it. I can see. I see one student, Himanshu.
Hello.
Yeah.
Yes, sir. Can I ask question? One.
Absolutely.
Sir, I have two questions. One is regarding the surface gradient, and could you explain? I mean, what? So I was not able to understand the idea of surface gradient from the video lecture. Could you re-explain this?
Okay. So the question is, how do we think about surface gradients? Correct? Huh? Well, mathematically, it's fairly similar to. I mean, it's not that different from a normal gradient, except that you're taking the variations only along the surface. So, so for example, if you have variations along x, if a quantity, let's say, imagine a quantity which is a function of space and time. Like, let's say a function of, let's say, it could be any quantity, let's say, velocity field. So velocity is a function of x and y. Now, if you want to compute the gradient in this two-dimensional space, then you would have the derivatives with respect to x and derivative with respect to y, and then that's how you construct the gradient vector. Okay, that would be del u by del x times the unit vector in the x direction plus del u by del y times the unit vector in the y direction. Right. Now, this gradient vector is something that basically determined by the magnitude of the two derivatives x and y. A surface gradient is the main one difference about the surface gradient is once you have a surface, okay, then you're taking a derivative only along the surface. Okay, so imagine a quantity where you have an interface and you have temperature variations on the interface. Okay, so you have surface of water, and then you have temperature variations on the surface of water, meaning from one point to another point, the surface temperature is varying, and the interface is absolutely flat. Okay, then the surface gradient is just nothing but the derivative taken along the variations of the temperature along the surface. Okay. What I can do is is there a way for me to write this? Are you with me so far on this, Himanshu?
Yes, sir. Yes, sir.
Okay, so I briefly discuss this, and I'm pulling out the necessary image for you to see. Give me a minute. Okay, so if we basically see something like I'll show you an image from week 2, and this is the final summary that we have. Let me share my screen. Okay, so you should be able to see my screen, and if we scroll down on this, okay, so here's a system. Here's a system that I'm trying to show. So here what I'm trying to show is instead of temperature, let's say surfactants, okay, that you can see on the screen. Are you able to see this, Himanshu?
Yes, sir. Yes, sir. It is visible.
Okay, so now if you see here, I have basically a scalar field. A scalar, in this case, there are two concentrations. One concentration is in the bulk that I've denoted by C subscript B, which denotes bulk. And the other concentration is on the interface, C subscript I, which is on the interface. And now if you take the surface gradient, now by definition, it is basically taken on a surface. It is not a gradient that exists in the bulk. So it is only on the surface. Now, if you imagine for simplicity that this surface is flat, okay, if you imagine that the surface is absolutely flat, then um, the surface gradient would be only variations along the surface. So imagine along the flat interface, along this flat interface, let us basically assume that, just one second. Yeah, sorry about that. So imagine if it's a flat interface, and if there is concentration variations along this flat interface, and if you assume that horizontal is x, then the surface gradient is simply del C I by del x. Del Ci by del x. Now, why is it del x? Because as it turns out, the interface is, if the interface is flat, then the derivative along the surface is basically the derivative along x. Okay. Let me see if I can. I just need to. The Zoom's window is actually blocking my view. So imagine a surface which is perfectly horizontal. I hope you can see this, Himanshu.
Yes, sir. It is visible.
Okay, in this case, the x is basically, in this case, the derivative here, the quantity that I'm interested in, variations along the surface, I can simply say s is equal to x. Okay, s is basically the quantity that is taken along the horizontal, and s is equal to x. So therefore, del c by del x, del c by del s essentially becomes the surface gradient is just the x derivative. Okay, but if the interface is actually curved, okay, and if the interface is curved, now let us say I have a curved interface like this. If the interface is curved, now you can clearly see that the derivative is a bit more complicated. Over here, the tangent is over in this way. Over here, the tangent is this way. So what I'm really looking at is I'm looking at the variations between a point here on the surface and a point here. Okay. Now I'm looking at variations along this curved surface. Okay. That quantity that I'm looking at is my surface gradient. Okay. So maybe I should just take a slightly. That quantity is my surface gradient. Okay. So the surface gradient, as it turns out, essentially in simple words, the surface gradient is basically the variation along the surface, and by definition, it is going to be along the tangent vector, because you're looking at variations only along the tangent. Is this clear? Do you want me to elaborate more on something?
No, sir, clear. It is now clear.
So surface gradient is just that it gives you the local tangent, but remember that the local tangent, to evaluate the local tangent, you need to understand how the interface is curved. So if it's a flat interface, obviously the local tangent is straightforward because it's constant everywhere along the surface. But if it's a curved surface, then you have to, that the local tangent itself is changing orientation. Okay. So the surface gradient vector will actually tilt, but it is always along the local tangent at that point.
Clear, sir. Clear.
Yeah. What about the assignment? Any questions from the assignments?
Sir, I have one question from week 3 regarding contact angle.
Assignment?
No, not. Sir, in assignment also I have one issue in one question regarding that had, but I have one question regarding contact angle week 3.
Yeah.
Sir,
please go ahead.
So
good.
Sir, so when you were discussing about the meniscus, so we had an example where we took a plate and we were inserting like that plate inside a fluid, and we had this meniscus shape, and so this solid boundary. But when we think about this, like for example, you showed this sessile drop over a surface in the video. So when we think of a sessile droplet over a, for example, let us say waxed surface or a hydrophobic surface, then the theta will become obtuse.
So you are referring to
week 3 in the photos that you showed, the photo that you showed. Actually, my doubt. Yes, sir. So in the example of a sessile droplet, so for example, if you have a waxed surface, so if you will have a hydrophobic surface, then the theta will become obtuse.
Yes.
But
theta will become obtuse when measured inside the droplet. Okay.
Yes, sir. Yes, sir. Okay. So the description that you had given for z equals to h of x, that description that we have taken and through which we have derived this formula of normal. And so, sir, if we draw it, then we realize that for a sessile droplet, which is standing on a hydrophobic surface, and for which the contact angle is obtuse, the theta is obtuse, then actually it comes out that that this definition that z equals to h of x will not be valid, because for one x we will have two z.
So are you referring to this issue? Huh?
Yes, here we had z equals to h of x, but if we have a sessile drop.
Okay, if you have a sessile drop, then you have to choose an appropriate coordinate system to define the curvature, local curvature. There is a bit of a disturbance, Himanshu, loud sound. Okay, so I can. Okay, there's no noise now. So if you're using a sessile droplet, like this, you'll have to use an appropriate coordinate system. For example, let me just make a drawing here, simple drawing. This is a surface, and then you're having a sessile drop, correct? Huh? Now you can choose this as the origin. Okay, and from here this is the point on the surface, and you can choose a vertical height. So what you're referring to is this is the radial. You can use other coordinate system. You don't have to use z equal to h of x. You can even choose r as a function of, let's say, theta, where theta goes from all the way from here. It goes all the way along the surface and reaches the other end. I mean, there are several ways several coordinate systems that you can choose to solve a problem like this. The shape of a droplet. I mean, you wouldn't just you shouldn't blindly take the shape that you have for this, and I mean the coordinate system. This remember this coordinate system of z is equal to h of x, meaning its variations of the interface position has been shown as a function of height as a function of x. It's being chosen for several reasons. One, it is a two-dimensional system. I'm choosing this coordinate system also in a way that they have chosen the origin here in such a way that when the interface becomes flat, okay, the origin is basically falls at the level of the origin. So meaning the z equal to 0 corresponds to the location where the interface becomes flat. Okay, you shouldn't straight away choose this coordinate system to for any problem unless you know that this coordinate system aptly fully describes the problem. Of course, if you directly choose a coordinate system without much care, then you'll run into the issues that you just highlighted, which is that you'll have issues of multi-valuedness and so on. You do get multi-valued ness several times, but that is okay. There is no requirement that the function should not be multi-valued. Okay.
It is clear, sir. So I just wanted to ask this, like, so when we are I wanted to ask this from this research perspective. So when we are trying to solve this in Navier Stokes equation, then do we include this Young's contact? So the effect of this Young's contact angle, what we have studied in week 3, explicitly into explicitly into the domain, or it comes implicitly? It should come implicitly through the solution.
Okay, so that actually, so maybe I can rephrase the question. There's something. Have you started looking at week 4?
No, sir. Week 4 I have not started.
Okay, so in subsequently when we do week 4, and you'll see the give me a, I think they will just load in a second. So if you see week 4 and you see I don't know if you can see the list of topics that are being covered. Okay. So we'll be looking at, I'll be talking about variational approach, week 4. And in week 5, in week 4, I'll be introducing this method of Lagrange multipliers. We'll be looking at shape of a droplet. We'll look at shape of a puddle. Okay. So this is sort of but these are all, remember, these are all static problems. Okay. So you have a shape of a puddle. These are all static problems still. Okay. Now, the question that you are essentially, if I understand correctly, the kind of question that you're asking is, if I were to solve the full numerical, full equations numerically, okay, which means that, let's say I look at equation, the week 2, there is a lecture on summary of all the equations. So these are all the equations. You have 2 fluids. You write down Navier-Stokes equations. In both the fluids, you write down the jump conditions and so on. Now you have to apply boundary conditions at the wall. Okay. Now in this case, there is no contact line problem. So therefore, there is no such boundary condition. But let's say you have a droplet and you're trying to impose that. You have a droplet on the surface and you're trying to get the Young's contact angle. You're trying to get the static shape. If you're looking for a static shape, this is the most important point. If you're looking for a static shape, then there are 2 possibilities that you'll encounter. In subsequent weeks, especially in week 4, you will realize this. There are 2 possibilities. Either the contact line position can be fixed, or the angle can be fixed. You can't simultaneously fix the angle and the position. If you simultaneously fix the angle and the position, then you're over determining the problem. Okay. So if you say that I have a flat interface and the angle is the Young's angle, then in the numerical simulations, if you say that, then you are not prescribing where the contact line is. You are letting the dynamics determine you are letting the equations determine the position. Okay, but you can also say I am going to fix the position, and I'm going to let the equations determine the angle. In which case, the Young's angle is not satisfied. Okay, so just to quickly reiterate, there is no absolute necessity that Young's angle is always satisfied. There are when we do subsequently the energy minimization problem, and we will do this systematically. Okay, we will derive the Euler-Lagrange equations and do the minimization. You will see that either you can fix the boundary condition you can fix the position of the contact line, or you can fix the angle at the contact line. You can't fix both simultaneously. So in a numerical simulation, if you say I am looking for a static shape of a droplet, then you have to make the choice beforehand. What am I in which context am I solving this problem? Is that clear?
Yes, sir. It is clear. It is clear.
But let me also reiterate. Some of these questions will hopefully become clear when you look at 1 or 2 more weeks. Okay, and then we can revisit this question again. If you ask me this question again, hopefully that will lead to some clarity. If you still have doubt, we can revisit this question again.
Yes, sir. Actually, using these equations, so in the numerical, just by brute calculation of these equations, we in the framework of level set, we did this simulation. But the result which came out, it was not very convincing because the shape of that interface was not coming out to be correct. So that is why I'm asking.
So it depends on what are you trying to compare it with. For example, if you do this with, let's assume that you're doing it in zero gravity. Okay, if you're doing it in zero gravity, that's a test that you could do. If you do it in zero gravity, and are you doing this? Is this a 3-dimensional simulation?
No, it's 2-dimensional.
Okay. So if it's because you can ask yourself, I'll give let me just slightly generalize it because it could be valid. Some of the other students who are watching this may be thinking about looking at 3-dimensional simulations as well. Or the same ideas apply to 2-dimensional system as well. Let's consider a situation. You want to test it. If you want to test it, to test whether your solver that you've developed is accurate, and you want to test it with some theory. One of the simplest cases that you can say is, I'm going to do it at zero gravity. I'm going to put a sessile droplet at zero gravity, and I'm going to say that this is the size of the droplet. Now, this is the angle. Okay. The moment you say this is the angle, let's say the angle is 90 degrees, then what do you think will be the shape of the droplet? It has to be part of a sphere. It has to be a hemisphere. Correct? Now, if you basically take the angle to be, let's say, 120 degrees, again, you should get a spherical shape. Except that it's a spherical shape. Hopefully, I can show this to you. So essentially, the only difference is this is the shape of the droplet. The only difference is that where you're cutting the angle. For example, if it's 120 degrees or something like this, you are cutting it somewhere here. Got it? That's the only difference. Okay. So you basically are removing this part. Okay. That should be the shape of the angle. This is a test that you can do. Is your code can it produce this? So here, remember what you're doing is you're fixing the contact angle. Okay, but now let's say I'm fixing the position. If I'm fixing the position again at zero gravity, here's my surface. If I'm fixing the position, and I say that my position is such that it has to be between here and here. Once you've chosen a volume, then there is no other option other than to have, of course, this is assume that this is a sphere, but once you've chosen a volume, you have no option but to have a sphere, a part of a sphere touching these 2 points. Okay, and what will be the shape? The shape of the sphere will be fully determined by what is the volume inside. So again, you can you can check whether this is something that you can straight away analytically derive. In fact, in subsequent lectures, I have actually given the formula for an interface in zero gravity by specifying any where the angle is known here at the wall. Okay, or the volume is fixed. Either the angle is fixed or the volume is fixed. I do this energy minimization in subsequent lectures, both from the perspective of an arbitrary curved interface, but also for a spherical curve. Okay. So you'll see it will become clear, these ideas. I think that specifically will come. Minimization, in fact, actually, the first thing that we do in energy minimization is I discuss the so-called method of Lagrange multipliers. Okay, you'll see that when it comes to, I'll show you an image. So, for example, something like this. This is a droplet that is sitting on a flat interface. You can also get images like this. For example, this is a small experiment that we've done in the lab, where if you take a wire mesh like this and you dip it into a bath, you get a shape like this. This is purely a minimization problem, and I discuss this minimization in great detail. Okay, so maybe we'll just have to wait for a few more days.
Yes, sir, I follow.
Okay, so yeah, so try to work out the assignments on your own, and if you're having any of you have difficulty, please meet me on these live sessions. We will be meeting every Saturday, India time at 11 a.m.
Sir, could I say one thing?
Yeah.
Sir, in the last in the last live session, it is my humble request that could you please take us through some research topic which are going on in interfacial fluid source in the last live session when the course ends in October?
Yes. Okay, so what I will do is I have, if you actually, as per the, if you wait and subsequently do the lectures, you'll see that week 12, I have week 12 I've left. I have basically focusing on advanced topics. Okay, the research in this area is very vast, and there are lots of aspects that are being investigated. I do look at some open problems, interfacial fluid mechanics, and especially the problem of contact line, a moving contact line is discussed, and what is the strategy, what is the modeling approaches that are being adopted by people. I discussed that. But yeah, what we can also do is I take your feedback. What I can do is during the live session on week 12, towards the end of in October, as you said, I could actually discuss some of the things that we do in my lab, some of the research topics that we explore, and some of the things that other people do during the live session. We could even have an extended live session if needed.
Yes, sir. Exactly. That's your group at IIT Hyderabad.
Absolutely, I'd be happy to discuss that. I mean, I didn't discuss that in the course because the course was supposed to be only mainly it was purely pedagogical in nature. But yes, the live sessions will give us an opportunity to discuss some of the problems that we are investigating in my lab, and that will hopefully give students like you and many others an opportunity to understand what kind of research happens in interfacial fluid mechanics.
Sir, actually, there is this first question. So in the assignment, actually, I think the options, no option matches. Sir. So there was this problem. Assignment 3.
Assignment 3 is it? Okay. I'll check with my TS. Okay. I'll make a note of it. Assignment 3, first question.
Yes. First question, sir, in which the divergence of n cap, the normal is asked. So none of the option matches. Sir, the equation is given as h of x equals to 4x square plus 5.
I will check that. I will check that. Huh? I will check this and I will get back to you. Huh? Yeah, thanks for raising this. Let me check. Yeah, okay. All right. So I think it's a good place to end the live session. Himanshu, I'll take a look at this assignment number 3, first question, and I'll revert back to you. There is I think we can introduce a correction if there is if it's needed. We are done actually our check, but maybe it could be some mistake somewhere. Okay, we'll again check. Huh? All right.
Yes, sir. Thank you, sir. Thank you.
Huh? All right. So then I think it's a good time to end the session, and